fairly well. Let's begin our lecture number 17, the final third of our course. And the scope of today's lecture is to demonstrate how to employ potential functions in magnetostatics to determine the final quantity, which is the field. And in order to do that, we are going to do some examples. And first, we are going to introduce the formalism of using potential functions to solving problems in magnetostatics. For instance, for linear media in which B and H are linearly related, we are going to consider the situations for J different than 0 by use of the vector potential, and situations in which J equals 0, then we can use a scalar potential, because in this case for J equals 0, the curl of H is 0, circulation of H is 0, and H can be derived from a potential function, scalar potential function. Then we can use a potential function. Then we're going to consider media having permanent magnetization and J different than 0. Also, as well, use of the vector potential and use of the scalar potential. And we are going to just indicate what happens if J is not equal to 0 for the case of the vector potential. You can use superposition to solve the problem, okay? You cannot use the scalar potential, but you can find the solution for J equals 0 using the scalar potential and make a superposition with the solution for J different than 0. And some examples. So we're going to talk about the formalism of solving the problems. Then we're going to do some examples. The references for this lecture are Jackson's chapter 5 and our ebook available at, it's always good to remember, right? The ebook, you can find it. I just said that in the first lecture, so let me just remind you. You can find it at this address, lsi photonica.ufpe.br, then my name. Then in my web page you have two, let me show you. That's the address. You go to this redirected to this page here, and these those two blobs here. This is a first part of the ebook and the second part. And in the first part, you have all the chapters, okay. As well, in the second part, you have 6 additional chapters. And if you don't speak Portuguese, if you don't understand Portuguese, you can open these books using the Chrome browser. Then you can translate through your language. So you can translate automatically the ebook and follow it, okay? So that's how you find it. Okay, let's get started. Let me just position my screen here. The first thing we want to do, well, let's consider the first case, the case of linear media with either J different from 0 or J equals 0. J different from 0, use of the vector potential. So let's consider that situation. So what's the formalism? Let's go to Maxwell's equations for magnetostatics. The divergence of B equals 0. So due to our properties of vector fields, B is a solenoidal field, can be derived from the curl of a vector potential, which is called A. At the same time, curl of H equals J, and given that we are talking about the linear media, right? So in this case, we have the media is described by a permeability. So this can be a piecewise situation, right? Piecewise situation. You can have two material media in contact with different permeabilities. So you can have J1 and J2 here, current distributions, you can have the mix. Of course, have insulator materials that has some permeability, and you have a current density, which is a circuit, in fact, that's in the vicinity. We are just representing abstractly like this. So you solve the problem in each region, and you use boundary conditions to solve. So let's assume for a single medium, how is the formalism? So you go use the linearity property and plug into the curl equation. Then you have this equation, curl B divided by mu equals J. Assuming a homogeneous medium, then mu can come out of the differential operation. Then you're going to have a differential equation for B. So I have a second curl equation for B, a second differential equation for B. The first one is divergence equals zero. So if I use now this condition here, the curl of A, so I insert into this equation, so I can have a curl of A equals to mu J. And also, because we can expand this, right? So just recall that curl of a vector, there's an identity, is gradient of divergence of A minus Laplacian of A. Okay, so that's the identity. We demonstrated that for stationary currents, this is equals to 0, right? We did that in a previous class. So we have curl of curl equals to minus Laplacian. So we have this final second order differential equation for A, and you solve that equation using the techniques that we derived earlier in previous classes, separation of variables and so on in each coordinate system. Then you solve the problem. We are going to show you how to do it in practice. We're going to do some examples. To solve this equation, the solution method is simpler when J has just one fixed direction. Okay, why? Because A is always resembles, the aspect of J. It looks like J, right? So if J is like this, A is going to be like this. If J is like that, A is going to be the spirit of J. So it looks like it. If J is constant, the direction is constant. J might be variable, but if the J direction is constant, A is also going to be on the same direction, and it's going to be easier to solve this equation. Otherwise, it's going to be more than one component, might be complicated to solve it. Not impossible, but can be solved. Let's consider now the situation in linear media, right? And special case in which J equals to 0. Then we can use the scalar potential. Well, because now curl of H becomes 0 everywhere, right? And then it means that I can define a potential function. This is called the scalar potential, phi m, magnetic potential, if you will. Then you can plug that into the divergence of divergence of B equals divergence of mu H for homogeneous medium, this is mu divergence of H, which is 0, right? So if you plug H here, you have Laplacian of phi m equals to 0. So in linear media, with J equals to 0, the scalar potential satisfies Laplace's equation, and we have all the methods we derived in previous occasions to solve that. We have now only to be worried about boundary conditions because we might have different linear media involved, right? So we might have medium 1 and 2. Okay, so boundary conditions are easy to derive. The first property is that the potential is always a continuous function at the boundary. So if I have a normal that goes from 1 to 2, the first condition is that the magnetic potential calculated on side 1 must be on the interface, let's call it sigma, equals the potential in every point of the surface, right? Phi m2 on the surface sigma. The second condition comes from the continuity of the normal component of B. We know that in whatever is the medium, normal B is continuous. So it means that B normal 2 equals B normal 1. We relate B equals to 0, right? We relate B to H, mu 2 H2 normal equals mu 1 H1 normal. And by, in turn, H equals to minus gradient of the magnetic potential. So the H normal equals minus the partial derivative of the potential with the normal direction. Okay, so that's what we have. So that's the second boundary condition we have to employ. The product mu times partial derivative equals to, I mean, this sign is going to be the same on both sides of the equation, equals to mu 1. In this notation, as always, xm, sorry, it's not xm, it's xn. Sorry about that. Xn is the normal coordinate. The coordinate that's normal to the interface. You know, at every point, define a coordinate that goes normal to the surface. For a sphere, that would be the radial coordinate. For a cylinder would be a radial coordinate, cylindrical coordinates. For a flat surface, could be the orthogonal coordinates. So this is a normal coordinate. Okay. So that's the boundary conditions. So that's how you solve the problem. Okay. You solve a second order differential equation, which is Laplace's equation. And if you have several media, you apply boundary condition according to those relations here. Okay, the second case, first case, linear media with vector potential or scalar potential. Second case, medium described by a permanent magnetization, Nj equals to 0. Let's make it. Let me see just quickly here. Just a second. Yeah, I think it's. Let me just fix a little bit the way we are doing this. I mean, this doesn't have to be J different than 0, okay? So the second case we are going to consider is media having permanent magnetization and J different from 0 also, right? Linear media, or media having, let's drop that thing here. Media having permanent magnetization, that's all, okay? I'm gonna fix this class notes. Let me fix on the original here. That's how we're gonna do it. So for J different from 0, we use vector potential. And for J equals 0, we can use vector potential either for J different from 0 or J equals 0. In fact, I'm going to do like this. Use of vector potential. And for the case J equals 0, we use scalar potential, right? So that's how we're going to do it. So here is for J equals 0. So we can use the vector potential whatever the situation is. J equals 0, J different from 0. So let's fix here. So the second case is media with permanent magnetization. Okay. First, let's consider use of the vector potential with J equals 0. Okay. So I'm going to erase this. First case is this case here. Okay. Let's assume that J is different than 0. So what happens? Then we're going to say what's the modification we have to do for J different than 0. So we have here J equals 0 again, curl of H equals 0. Also divergent of B is 0, B is solenoidal, so B can be written like this. Okay. So if we go to the curl equation, curl of H, and use constitutive relation, recall that B equals to the constitutive relation for magnetic medium is mu0 H plus M. So H can be written as B divided by mu0 minus M. So curl of H equals to curl of B divided by mu0 minus M, right? So let's go back there. So that's what we have. We have this equation here. So we separate the terms. So M is given, B is the unknown. So we have a curl of B under something given on the right hand side. And then we go again, right? Curl of H, recalling divergence of A equals 0. So that's Laplacian of A minus Laplacian. So that's going to be if I plug this here, curl of B is this equation. Here's mu0 Jm, but Jm is this thing here. It's curl of M. It's the magnetization current. So we have a second order differential equation, non-homogeneous, in which you have Jm on the right hand side with Jm given, because you know the property M is given. Okay, M doesn't depend on the field. M is something that's independent. This is the case for permanent magnetization, in which you saturate the magnetic material. So if you change the field, the magnetization doesn't change. So we have some type of material that is permanently magnetized. Okay. Have a ferromagnetic material in which you saturate the material. So you are working on this region here. Let's call this H and this M. So M is always constant. Whatever you do with H, nothing happens. Even if you have an hysteresis, the hysteresis is not going to reach the region, the saturation region. The saturation region, M is very well defined as constant. Okay, so that's the region we are talking about. So this is the situation we're talking about. So Jm is a parameter that is given. So I mean, we know the solution for this type of problem. Okay, so the solution is simply a volume integral involving the magnetization current, and that gives a contribution on the surface that arises from, I mean, here you integrate on a finite volume, right? That's how you have to do it. If you integrate in the whole space, the second term is not required. If you just integrate on the volume, then you separate one contribution due to the volume and another one due to the discontinuity of M on the boundary. So we are going to have this integral. Okay? So that's the solution for J equals 0. What happens for J different than 0? All you have to do, so you can simply change the right-hand side of A. We have Laplacian of A equals to minus mu Jm, right? We just change Jm to J effective. That's all you have to do. So we have now Laplacian of A equals to minus mu J effective. What is J effective? Well, J effective is the free current density plus the magnetization current density. And that's what you have to do. Or, if you want, you solve by superposition, right? You do a superposition of our results, because we are assuming that these quantities in the problem, they are independent. If one affects the other, then we cannot do this principle here. But if one is independent of the other, you can simply add, I mean, if J and Jm are given, even if one influences the other, I mean, but if they are given, they are fixed, they influence the field, but not each other. Okay, so one doesn't change the other one. J is given independent of Jm, and Jm is given independent of J. So you can use superposition. You can solve one problem with Jm not 0, J equals 0, and the other one with Jm equals 0 and J different than 0. So two problems, and add the solutions. No problem. You can do that. Or you can simply substitute in the formulas Jm by J effective. So here what you have to do is just replace this one by J effective and this one by K effective. Because if you have some surface current density due to free carriers, you have to add that term too, if you don't do the integration in the entire space. Okay? So that's what you do. Okay? So these are the two alternatives. You either solve the problem completely at once, or just separate into parts. Sometimes it's easier to figure out the solutions. The solution of one problem alone is easier to determine sometimes. So you can solve like this. Okay? Now, the second situation is when J equals to 0. So this first one was materials in which M is fixed and J is whatever, 0 or not. But in the second case, is materials in which M is fixed, they are not linear media, right? These are ferromagnets in which the magnetization is saturated. So you have now the second case in which you have, in this case, J equals 0 and M is different than 0. So if J equals 0, curl of H and M is given. non-linear medium with M constant independent of the B field applied or H field applied. Curl of H equals 0 means that H equals minus gradient of the potential, scalar potential, and divergent of B equals 0. And again, constitutive relation, right? So you're going to have divergent of H, right? As I did before, right? H is right here, somewhere here. So we're going to have divergence of B. Now I'm going to use this one. Sorry, let me erase this thing here. We're going to have divergence of B, which is mu0 H plus M. Mu0 is a vacuum permeability is equal to 0, so it means divergent of H equals to a given parameter, which is the minus divergent of M. Okay? So we define this fictitious magnetic charge density. It's a fictitious parameter. It's as if we had a magnetic charge for H, not for B, right? B is a field that there's no magnetic charge. But I mean, for H, you can pretend there's a fictitious charge. Why? Fictitious charge. Why? Because all the methods we employ to solve Poisson's equation for electric charge density can be employed here. Same behavior. H field is going to have the same behavior of the E field. The scalar potential for the magnetic charge density, this fictitious magnetic charge density, is going to have the same behavior. So I define this to be very, very similar. We are not going to have a permittivity, but we can define a rho m magnetic charge density equals to minus divergence. We keep up the signal to have the same behavior of the scalar potential for electrostatics. So we're going to have a Poisson's equation now. Laplacian of phi m equals to minus rho m. And then the equation for H, if you see here, right, is equals to rho m. So it's like H was the flux density vector, the electric flux density vector in electrostatics. Same behavior. For instance, the flux of H outwards and its closed surface equals to the magnetic charge involved, enclosed by the surface, which is the integral of this. So all the properties we have are those. And also boundary conditions, well, very similar to the flux density vector in electrostatics. We're going to have continuity of the magnetic potential and discontinuity of the normal component of H, which is going to be the surface charge, magnetic charge density, this fictitious parameter that we define. Okay, and just notice. Let me just do it here separately. Rho m equals to minus divergent of m. Okay, if I go to the boundary, make a volume integral of rho m, and it goes from 1 to 2, right? For a cylinder of height h, an area delta sigma, the volume integral of rho m dV equals to the total magnetic charge enclosed, fictitious charge we're talking about, so if you integrate this and use Gauss's theorem, this is going to be minus flux of m on side 2 minus m on side 1, right? Because we have the surface on top, the surface on the bottom, times the sigma, plus a contribution that is something that's proportional to the height. If making in the limit, if this has a limit, of this quantity, this term is going to go to 0, and this is integral. Well, the sigma is so small that simply the product of the quantities is going to be something like this. So the magnetic charge, this is equals to that, right? Magnetic charge is going to be minus n m2 minus m1, right? So that's what it is. I'm sorry, there's the sigma here, delta sigma here, I forgot. So let's call, let's call the quantity of charge related to the area, right? Delta Q magnetic. So I have here delta Q magnetic divided by delta sigma equals to minus n dot m2 minus m1. This is gonna be is this right? Yes, this is right. Okay. So this is the surface charge density, the magnetic surface charge density on the surface, the fictitious one. Right? So that's the boundary condition for for M. Rho M S, in fact. Okay. Or if you want, if there's a discontinuity, it means that you have a residual magnetic surface charge density given by minus n m2 minus m1. I'm doing this because I want to show you what happens when you have simply magnetic medium and vacuum outside, okay? So medium 2, m equals to 0, medium 1, m1, m2 equals 0, m1 equals to m, okay? So the boundary condition is the magnetic surface charge density equals to m2 dot n equals 0, m1 dot n equals m normal, with the minus sign, it's going to be minus m2 dot n, which equals to m1 dot n, which equals to m dot n. So the surface charge density when you have vacuum and material medium equals to the normal projection of the magnetization on the surface. Very similar to the bound charge in electrostatics, right? Rho Bs equals to the polarization component along the normal direction. Same thing, same behavior, right? So in most situations, you're going to have vacuum and a hard ferromagnet, which has a fixed magnetization. So in summary, these are the conditions. You're going to have, so magnetic charge is very similar to polarization charge. Okay, very similar. The equation is the same that defines the divergence of M minus divergence of M is the volume density of magnetic charge. This type of magnetic charge we are defined here to make a similarity with electrostatics. So we have then continuity of the magnetic potential and a discontinuity on the normal component of age, which is due to that residual magnetic surface charge density. If medium 2, as I mentioned to you, if medium 2 is vacuum, the boundary condition is going to be n H2 minus H1 equals to rho ms, which is equals to m dot n, right? For medium 2 is vacuum in this case. Okay? So these are all the formalisms we have. We are going to solve now a couple of problems using either one or the other method. Okay? Just make it a formal solution, for instance, in this case, just to show how is the integral solution before you go to a practical problem. Assume that you have a magnetized volume in vacuum. As we just mentioned, most of the problems is going to be a hard magnet, you know, with saturated, immersed in vacuum. Somehow we gave that state, we magnetized the material in lab, saturated, and we are using that magnet. We want to know what's the field around. So that's the situation. We have a piece of material with a volume V with magnetization that's well defined. So the potential is going to be the solution of Poisson's equation, as we did before. In the volume, we have a magnetic charge, rho m. So there's no permeability constant or permissivity because the equation doesn't have any constants. So there's just the traditional rho m divided by 4 pi magnitude parameter in the denominator, x minus x prime. And on the surface, we are separating, right? We are just integrating on the volume. On the surface, we're going to have a rho ms, which is the magnetic surface charge density on the surface. And replacing this by the definition, rho m equals to minus divergence of m. And on the surface, as I told you, if the outer medium is vacuum, on the surface you have rho ms equals to the projection of m. Okay? Just to show you the similarity in the electric and magnetic cases. That's what happens in the electric case. Right? Rho b equals minus divergence of the polarization. Rho bs is the normal projection. In the magnetic case, you have the same thing. Every time you have the external medium is vacuum. We would have an equation that's similar. Have different material outside. We have two different materials. We would have a very similar equation in which you have a discontinuity of P, normal P, minus the discontinuity equals to rho bs. It's the same as the rho ms. Okay. Now, it's always important to recall you. I want to read this sentence here. If integration is carried out in the whole space, using only the volume integral. You don't have any surface integral because the whole space, the surface integral is at infinity, and at infinity the fields are already vanished. Okay. So the surface integral is the result of integration in the whole space. It's the same result. Take into account the sudden change of the magnetization function on the boundary. Right? So I have a sudden change. Magnetization suddenly goes to 0. This derivative is taken into account in the divergence of m, which is the magnetic charge density. That's what originates the surface term. We break into a volume, finite volume integral and a surface integral, or we integrate the whole space, just the volume integral. It's the same result. Okay? So, if we consider this, suppose that we integrate in the whole space, just recalling this thing is important to reinforce it. Okay? We use the chain rule again, right? Divergence of a vector times the function equals to vector times gradient of the function, which is the inverse function, plus function divergence of the vector. Also that famous property we always use, nabla prime equals to minus nabla of the inverse function. Then if we do that, I ask you to do it the demonstration. I'm just going quickly here. we are going to have two terms, right? We're going to have two terms. Then we would have a surface term that arises. Well, if we integrate in a finite volume here, we would have only when m is different from 0. And here we would include, you wouldn't have this thing here, you would go to the boundary and integrate that. Either that or you integrate in the entire space. Okay? So if you integrate in the entire space, the surface integral is at infinity. And at infinity, this thing here is negligible. Okay? It goes to 0. Because, I mean, everything falls off faster than 1 over r squared. Area increases with the square of the r squared. So the sigma goes with r squared, right? M goes with the inverse of r squared, but there's another r here, so there's r cubed. So this thing goes to 0. Okay? Also, so just showing you that if I break into a finite volume, I have to include the surface integral. If I go to the entire volume, the surface integral is at infinity, and it's going to be 0, the result. Also, it's interesting to look at the asymptotic behavior of this expression, right? So, which is the first integral here. What's the asymptotic behavior of the scalar potential? Well, what we have to look at is when you are at very large distances, x prime in the integral is practically constant. Okay? I mean, when you change x minus x prime is always, I mean, if I calculate at this point or this point or this point, it's going to be the same. Because let me make an exaggerated picture here. This is the volume, right? So I'm changing x prime in the integral, but x prime doesn't move around if x is very large. So x prime is negligibly, doesn't change at all. So this thing here, this nabla here, can go out of the integral. So it's as if the inverse function was simply 1 over magnitude of x. This is not very right, okay? So that's not correct. This is incorrect. I mean, this is for x prime equals 0. I have to fix that. This equals, there's no approximation here. So just, you just have to say like this. Is independent of x prime. Why? Because x prime is always fixed at the center of the volume, right? So let me fix here, page 7. Here, this is wrong. Well, look, I wrote this thing here, then I didn't pay attention, but I mean, looking again, I mean, x prime is different from 0, you know. X and x prime might be same size vectors, but if I change x prime doesn't change. That's what I want to say. Okay, so what we have to say here that is independent of x prime. X prime is a constant vector, doesn't change in the integral. So what it means is that you can remove this gradient from the integral. It can go out, comes like this. Then you have integral of m dv, which is the magnetic dipole moment of the volume. It's like a small point dipole having magnetic dipole moment equals to little m. So all we have to do is to calculate the gradient of this thing here. Is easy. So that's what we have, right? Dot product of the magnetic dipole times the gradient. Gradient of this is known, is the difference vector divided by magnitude cubed. So we're going to have the result that's very similar to the one in electrostatics. M dot the normal versor divided by r square. Here, r equals to magnitude of x minus x prime. Okay, so this is r. And AR equals to r divided by, well, equals to x minus x prime divided by magnitude. So what we have, that's the behavior of a magnetic dipole, right? A point dipole is going to have a magnetic potential which is similar to the electric potential, right? In the electric case, we had, P dot AR, then we will have an epsilon 0 here. So the behavior of the magnetic field lines of a magnetic dipole is similar to that of the electric dipole. So if we calculate H is going to be the same field configuration, as the electric dipole. So is that classical expression for the electric dipole? We would have here E equals 1 over 4 pi epsilon 0 r cubed 3 p dot AR times P times AR, sorry, minus M, minus P, sorry, minus P, right? And B is just, in vacuums, mu 0 times that. So all the field configuration is the same, right? So we have a dipole, magnetic dipole, and an electric dipole. They have the same field lines, asymptotically speaking. Of course, the lines are not the same close to the dipole, because the B field lines close themselves, right? And the E field goes from the positive charge and starts on the positive and ends on the negative charge. Let's do some examples. First one, a thin slab with uniform current distribution. Suppose you have this geometry, this geometric construction, in which you have a plate that occupies, a region in space which ends on flat surfaces, okay? So the entire, you have a sheet which has a thickness which is H. On this region of width or height, let's say H, you have a uniform current density given by this function here, which is not shown here, but it's going to be a constant density along the x direction. So the question is, we can solve this directly by Ampere's law, or you can solve the vector potential as well. That's how we're going to do it, okay? That's the front view. It's as if we had several wires, straight wires in parallel, stuck on this region that has a height h. So the current density is given by this function here. It's constant in the region, the surface, the region ends on the surface z equals h over 2, or z equals minus h over 2. So current density is 0 after that, outside, right? So in this example, J has a fixed direction. So does H. H also has the same direction, because H, in this case, due to the formula that relates A to J, A is going to be parallel to J. Also, we have some symmetry here in this problem. We have symmetry, translation symmetry relative to the x and y coordinates, you can see that you have symmetry along the x direction and symmetry along the y direction, right? Potential, vector potential depends only on z. And vector potential satisfies that equation that we mentioned to you before. So, and vector potential has only the same component, x component, which in principle depends on z. So what is the equation, right? Well, when we have a current density, the equation is Laplacian of A equals to minus mu 0 j. Notice that in this example, the permeability is constant, either inside, the permeability is mu 0, or outside. If that wasn't the case, if I had a different permeability, then I would, you know, solve piecewise the problem. Right? It would be more complicated. I mean, not more complicated, but it would be more algebra. But that's the equation we have everywhere, right? Only that j is 0 outside. So what happens? A is going to be a vector that has only the x component, because j has only an x component, right? So this is j equals to jx ax, which is 0 outside of the region and not 0 inside. So this is going to be Laplacian of ax equals to minus mu 0 jx ax. So in this case, the Laplacian of a vector is simple because the vector, the versor, is constant. So you're going to have a scalar equation. Laplacian of ax equals minus mu 0 jx. Okay? So in this case, ax equals to a function of z. So we are going to label, as in the class notes, for magnitude of z smaller than h of 2, so inside of the current distribution, a equals to a1 of z times ax. For z larger than h over 2, a equals to a2. And for z smaller than minus h over 2, a equals to a3. So above is the region 2, and below the plate, let's say, is a3. Okay. So let's solve the non-homogeneous equation. Inside, j is constant. The Laplacian of a function that depends on z, second derivative, equals minus mu 0 j0. And outside, the Laplacian outside, nabla 2 of a2 or a3 equals 0. So it means that the second derivative of a2 or a3 dz squared equals 0. It means that a2 or 3 goes with a linear function, right? Linear function of z. So we use the solution with c and d constants on the upper region and e and f constant on the lower region. Also, we have to consider that looking at the geometry, let's make it thin like this. That's the lane. I have a lane here of current, right? I have this thing here. Well, because J has the same direction of A and J have the same direction, right? So this is Y, Z, and X is coming out of the screen. So here, the field at a certain distance, the A2 and A3 are the same magnitude by symmetry, right? above the region and below at the same distance, A2 equals to A3. So we have this property, right? A2 of Z equals to A3 calculated minus Z, symmetry. So if you do that condition, so you're going to have the A2 is Z plus D, and A3 at minus Z is minus Z plus F. So we rearrange, we have a linear equation for any Z, C plus Z times Z equals to D minus F times equals 0. So it means that E equals minus C and D equals to F. In other words, we don't have to solve below, right? Just have to solve for Z larger than 0, because the solution below is going to be automatically obtained because we know the solution above. So A2 can be written like this and A3 like that. So in general, for Z outside of the current region, okay, the only thing we have here a changing sign. This doesn't change. So the potential vector can be written like this: C, absolute value of Z plus Z. Also, inside, A is an even function due to the condition A parallel to Z. So inside, if you use the Z larger than 0, so the solution inside at minus Z, if you use that solution at minus Z, it has to be the same at Z, right? So if we, I didn't show the solution here yet. Did I solve it? I just skipped that solution. The solution inside, general solution, is doing by repeated integration, right? First integration is a linear function plus a constant. Second integration gives the square, dependence on Z over 2 plus a linear plus a constant. That's the solution inside. So the solution inside is this one, right? At minus Z, at Z, right? Or at Z or minus Z, it's going to be a minus here, plus AZ plus B. So if we change the sign, those have to be equal. We cancel B. This term is crossed out, so we prove that A equals 0. So for A to be an even function inside, A has to be the little a, so lowercase a is going to be 0. Okay. So we have the general solution outside, above or below, but you can use that one above only. And inside we have to just eliminate the second term here. You're going to have a solution which is going to be like this. So in other words, A1, so recall, A equals to A1 AX for magnitude of Z smaller or equal to H over 2, and A equals to A2 AX, A23, right? For magnitude of Z larger or equal than H over 2, because the function are continuous. Inside is going to be minus mu 0 J0 over 2 Z square plus B. So A equals 0. That's what we proved, right? And outside, the solution is going to be C magnitude of Z plus D. Okay, that's the solution. We only have to work outside, up in the upper hemisphere only. Okay. So we have three constants, right? We can determine two constants only from the boundary conditions. So we can do that, and one constant is going to be undetermined. But is that a problem? Well, if you consider that the H field is, or the B field is equals to curl of A, this constant, whatever is its value, is not going to affect the B field. So I can set this third constant that's going to be undetermined to an arbitrary value. I'm going to set so that I make this term here equals to 0. So I'm going to subtract D everywhere. So it's going to be B minus D and D minus D. This is going to be 0. This is going to be a B prime, which I call back again to B. So the solution is going to be proposed like this without loss of generality, okay? So that's how we solve the problem. Otherwise, we would have this constant D everywhere, you know, until the end. Then when we make a derivative, the D goes away. We don't have to keep it D all the time. Just remove it. So that's the solution. Now we go to boundary conditions. Okay. So boundary conditions at Z equals to H over 2. A1 equals to A2 because vector potential is continuous. So all we have to do is to make Z equals to H over 2 in these expressions. And the second condition is that the H, well, H, we don't have any component normal to the boundary, but we have tangential to the boundary. H, you know, the tangential component of H, in this case, there's no current density on the surface. So K equals to 0. So the boundary condition is Kn cross H2 minus H1 equals to 0. So it means that H tangential 2 equals to H tangential 1. How do we obtain this? Well, B equals to everywhere, right? B equals to mu 0 times H. So this is curl of A. So we can from A determine, you know, H. So H equals to 1 divided by mu 0 curl of A. So, and A has only component X that depends on Z, AX. So this is equals to 1 over mu 0 ddz AX. So Z cross X equals to AY. So H field is in the Y direction, right? So that's how we make the boundary condition for H. So if H tangential is continuous, means the Y component, right? Y component is continuous across the interface. So it means that at side 2, this constant is going to be the same on both sides of the equation. So I can say dA2 dz at Z equals H over 2 equals to dA1 dz at Z equals H over 2. So in other words, what do we have here? We have two constants to be determined. We need two boundary conditions. One boundary condition is this one here. A1 equals to A2. Second boundary condition is derivatives of these functions have to be continuous because mu 0 is the same. So it's a linear system. Then the solution is outlined in the class notes. Okay, you obtain these results. Let's see, where is it? After some calculation, you go and do that for me. That's the result we get. Let me see. That's the vector potential. Has the quadratic dependence. What is this H2 here? Okay. Yeah. We have a B that's different from this. Then we have that thing here. And outside, we have a function like this. Notice I didn't mention to you, right? Well, let's just take a look here. If you look at the numbers here, if you calculate the curl of A, you have B, right? That's the B field. The B field has this behavior. It points to one direction above the current region, and it points to the other direction. It points to the left. You have a current that comes out like this. The B field is going to be like this, constant, right? Everywhere outside, like an infinite plane. And below is going to be like this, as we expected. Inside, we have a linear variation of field relative to Z. So at Z equals 0, the field is 0. It's to the left above and to the right below. It has a transition exactly in the middle of the region. Right? So that's the behavior of the field. So there's a continuous transition. That's for an infinite plane. What you have to do is to just shrink this region so that it becomes a plane. So what's going to happen is that you are going to have a sudden discontinuity. But to have a finite thickness is not really a discontinuity, right? It's a continuous transition from one to the other. Okay? If you look at the A function, that's how it looks like. It's a quadratic function in the region. This is plus h over 2, and here is z equals to minus h over 2. This is a plot of ax times z versus z. So this is a quadratic function. There is a linear function. Here is the magnitude function, magnitude of z, right? So you notice that we have a continuous and a continuous derivative, because the continuous derivative is the H field tangential, which is continuous. Okay? What I didn't mention is that as z goes to infinity, so does the vector potential. Vector potential for this problem is not finite for a large z. It's infinite, but it's infinite in such a way that the H field is constant, or the B field is constant. Okay? It's that type of potential for a uniform field at infinity. We can allow the potential to diverge in such a way that the field is constant. So that's what happens. So the only situations that we have a constant field outside is when you have a surface current on a plane, or a current, having whatever behavior you have on an infinite region. You can have even a variable current density, but outside the field is going to be constant everywhere, even at infinity. Of course, those distributions are just idealizations. They cannot be synthesized in practice. Okay? Next example I'd like to talk about is, now we're going to use the scalar potential, because we're going to have a problem in which we have a linear system, two different media, and no current density, no free carriers. So we can use the scalar potential. Okay? So here's the problem. We have a field that's uniform, then I put a permeable sphere of radius A in this region. It's going to distort the field, but the field is going to be uniform far away from the sphere. Okay? So in this case, I'm going to use the Laplacian of the scalar potential. Now, in this case, the boundary condition is that we have an applied field which is constant. Let's say that this is the z direction. So far away from the sphere, the field is constant. So let's use the scalar potential in this case. A is going to be minus gradient, and the Laplacian of phi equals 0 because divergence equals 0. So we have a solution for Laplace equations inside and outside of the sphere. We know that this problem, the potential depends only on two coordinates. Let's just put it like this. Okay, so put the center right there. Let me draw here of the points. So that's r, that's theta. The field is applied along this direction here. Okay. That's h, away from the, in the absence of the sphere. H equals to h0 az. This is the z-axis. So we know that for the symmetry of the distribution, I can make symmetry operations. We know that the potential doesn't depend on azimuthal coordinate, it depends only on r and theta. And we know that Laplace's equation, when potential depends on r and theta, is going to be Legendre polynomials times the power function. So the general solution, we have two solutions, one inside and one outside. So the solution either inside or outside is that expansion that we well know already. R to the L, R to the minus L plus 1. So we have to consider when you have to use one or the other one. We already solved this problem before for the dielectric sphere in uniform field. We know that we only need the L equals 1 term. Okay, we don't have to use other terms. Just why? Because far away, the boundary condition is that the field and this can be obtained from a scalar potential which goes linearly with z. In other words, goes with r cosine theta, because the derivative of this function gives a constant field. So the dependence of the potential far away is on cosine theta, which is P1 of cosine theta. So this is a problem in which the solution has only one term, L equals to 1. You can use all the terms if you want and solve the boundary condition. You're going to demonstrate that you only have L equals 1. So that we are going to use that solution. Inside, r raised to the first power, then we would have r to the minus 2, but we have singularity if we had that. So we will avoid using the r equals minus 2 term, because we have in the domain the origin. So inside the solution is the linear solution. Outside is going to be the linear solution, r cosine theta, plus the 1 over r squared. So we have, here we have 3 constants. Okay. One constant is the boundary condition at infinity. The derivative goes to this term, the derivative relative to r, okay, or z, right? You can make a derivative relative to z. So the gradient of the potential, you can calculate it. This term is going to give a 0 contribution for r going to infinity. So it means that you can determine A2 immediately. A2 equals to minus H0. So we have only 2 constants left, which is A1 and B1. Then we have boundary conditions on the surface. Just remember, boundary condition at r equals A equals magnetic potential 1 at R equals A equals to magnetic potential M2 at R equals A. Okay? First condition. The other one is normal B normal is mu, right, times H equals to minus mu gradient of magnetic potential. So we have a boundary condition that has mu times the normal derivative of the potential of the boundary is continuous. So it means that mu d phi m dx and the m2 equals to mu 0. I'm sorry, mu 0 outside and mu inside. X, I'm sorry, this is X normal. In this example, X normal equals to the radial variable. So what you get is this boundary condition here. Where is it? This one here, right? For any theta on the surface from 0 to pi, so we can apply those two conditions. So we have a set of two equations of two unknowns. So you can solve it and determine the constants. Okay? So here's an outline how to solve it. I'll leave it to you to work it out. So that's what we get. That's the result for the scalar potential inside. So inside this is R cosine theta equals to Z, right? We just did like this because we want to emphasize the uniform field inside. So let's interpret what are those things here. Okay, this is the internal field, is the coefficient of the potential, because the field is the derivative in Z. The field is directed along the Z direction. So the internal field, let's call it like this. Internal field equals to 3 divided by mu r plus 2 H0. H0 is the applied field. Okay? So I want to determine what is this term. Of course, this is the dipole field, okay? Because it changes with the angle cosine theta, and goes with the inverse square law. Right? So we want to relate the magnetic dipole. I mean, the internal B, everything in the Z direction, right? The magnetization, let's say B, internal B is in the Z direction equals to mu 0 H plus M, right? That's inside. So, but internal B equals to mu times H equals to mu 0 H plus mu 0 M. So I can divide by mu 0, so we have mu relative minus 1 times H equals to M. But H is the internal field. The internal field is this thing here. So the magnetization is equals to, 3 mu r, 3 times mu r minus 1 divided by mu r plus 2 times H0 AZ. That's the magnetization. And the magnetic dipole has a moment which is the integral of this on the sphere, but this is constant. So, well, just remember, it's important to mention, magnetization in the sphere is constant, right? Uniformly magnetized. So it's going to be 4/3 of pi a cubed. So mu r minus 1 divided by mu r plus 2 h0 az. That's the magnetic dipole moment. So if you go and look at the expression here, right, let's relate that. You see we have the mu r plus minus 1 divided by mu r plus 2 h0 a3. So this term here is the term that is in that factor there. So this term here equals to m times 3/4 3/4 pi az, right? That's what we have. I mean, the factor is just the magnitude. 3m divided by 4 pi, that's this term here. So the magnetic potential outside equals to minus h0z then we have plus there's a missing 3 here. I think I forgot a 3 somewhere. Sorry. What is the 3? Oh, that's what the 3 is. Oh, I'm missing I had to cut off a 3 here. There's 4 pi here. Sorry about that. So the 3 times the 4/3 of pi a cubed. So we cut a 3. There's no 3 here. So that's going to be m divided by 4 pi. So if you look at the potential, it's going to be a3 mu r. So that's what we have there. It's going to be m cosine theta over 4 pi r square az. So this is the potential due to a dipole m ar divided by 4 pi r square. So that's a dipole field, dipole potential, which is going to give a field. So the field outside, external field, equals to that to the applied field plus age of the dipole field. What's the age of the dipole field? Well, this is constant equals h0 az. The dipole field is given by one divided by 4 pi r cubed. That canonical expression. 3m dot ar minus m. If you calculate the gradient of this function, it's going to give a uniform field plus a dipole field, which has that classical behavior there, right? That calculated the derivative in r and theta. We're going to have this result here. So the sphere becomes outside as a dipole at the center, a point dipole, which has the exact expression, outside the expressions are the exact expression of a point dipole, right? Either for the potential or for the field. So just to conclude the lecture, let's make now a final example, slightly different, in which we have a magnetized sphere. Let's see, yeah, this one here, right? Again, let's use the scalar potential, magnetic potential, because we don't have any current, any free current in this problem. So we have now a magnetized sphere. There's no applied field outside. We have a magnetized sphere, and what's the field produced by that? Well, we know that the result is going to be uniform field inside and dipole field outside. But let's do it. Okay? Let's use the concept of magnetic charge now. So the sphere is going to be replaced by the equivalent of volume charge density, which is minus divergent of m inside, right? So we're going to have to replace minus divergent of m. We replace the sphere by a distribution that on the volume is given by that. On the surface equals to m dot product with the normal direction that points outwards of the sphere. Well, if the magnetization is constant, this is going to be 0. And here, if we have, let's call that z, I'll put it like this, that's theta, that's m is like this, m, so m is constant. The normal outwards is AR. So rho ms, the magnetic charge density on the surface, is m0 az AR, which is m0 cosine theta. Right? So that's what we have. So the potential anywhere can be written like potential equals to integral on the surface, because we don't have volume charge. So it's the sigma prime rho m on the surface. That depends on theta, right? But it's going to be on the integration variable theta prime divided by 4 pi x minus x prime. So let's prove that we're going to have the potential, anywhere, inside or outside. So this is going to be the sigma prime m0 cosine theta prime x minus x prime. You can use the sigma prime equals to a2 the omega prime equals to a2 sine theta prime d theta prime d phi prime, right? And integration is 0 smaller than theta prime smaller than pi, and phi to pi. Okay. Then we have, well, I'm going to just use the notes. We have that already prepared. So that's the type of integral we have. So we remove the constants m0 square and 4 pi outside of the integral. We have an integral that involves this and the inverse function. In the lecture, in the class notes, we have used the addition theorem, okay, to calculate the integral. And I'll let you follow the lecture notes. I'm going to make it a little different. I always forget to put, I had to leave the room, and when I came back, I forgot to put the scene here. So I'm sorry about that. About 18 minutes, I think, or more. Maybe 20 minutes without a good audio, so sorry about that. So in the lecture notes, we have we are using the addition theorem, okay, for spherical harmonics. Can use that to calculate the integrals because we're going to have some orthogonality properties. I'm going to make a little difference. I'm going to use the addition theorem, but you notice that, I mean, we don't have to do integration phi because potential doesn't depend on phi, right? So you don't have to involve all the that's like shooting with a rifle instead of a little, this is a very simple problem. Doesn't have to be like this. Okay, so I'm going to show you an alternative way of doing it. So the integration we have is this one. D phi prime, right? D theta prime sine theta prime cosine theta prime. So the m0 divided by 4 pi square outside. Then we have the inverse function. What we're going to do? Well, let's solve on the z-axis. Then use that property. After you solve the z-axis, just multiply each term in the expansion by the PL cosine theta. So we have the solution. So on the z-axis, theta is going to be 0, right? So x is going to be ZAZ. X prime is going to be R prime, AR prime. So the inverse function can be expanded in this case like this one. Smaller r over L, larger r over L plus 1. So we have a PL or cosine gamma here. Gamma is the angle between x and x prime. So in this case, gamma is going to be theta prime, because theta equals 0. It's the angle between zx and x prime. X prime subtends an angle theta prime. So this is going to be sum between L equals 0 and infinity, r smaller over L, r larger of L plus 1, PL cosine theta prime. So that's how we find, the result on the z-axis. So the integral we have is this one here, solved with expansion, right? So let's go here. So we have something like this. Integral from 0 to pi sine theta prime cosine theta prime sum r smaller over L, r larger over L plus 1. So we're going to have PL, I forgot, PL cosine theta prime. Sorry, but I forgot something here. This is not, well, just a second. Yeah, that's correct. PL cosine gamma, right? PL cosine gamma. Yeah, that's correct. PL cosine gamma. So it's cosine theta prime. So we have this integral, which is going to be integral from 0 to pi. Well, I can remove the arm smaller and larger, like this. Then I'm going to have integral from 0 to pi. So this is d theta prime here, right? So d theta prime. So we have cosine is P1 of cosine theta prime times PL cosine theta prime sine theta prime. Well, if we make the change of variables, x equals to, cosine theta prime here. x equals sine theta prime, right? Cosine theta prime dx minus sine theta prime theta prime. So this is going to be an integral between minus 1 and 1 of dx p1 of x pl of x, right? Of course, this integral is only non-zero when L equals 1. So it's going to be delta of L1 integral from minus 1 to 1 of P1 of x squared. P1 of x equals to x, right? So dx. So this equals delta L1 integral of x squared dx minus 1 to 1. So it's equals to delta L1 times x cubed over 3 from minus 1 to 1, which is 2/3 to delta L1 over 3. So in the z-axis, the result we get is this integral here. Let me go back. So the potential is going to be the result of the integral is going to be only the L equals 1 term, okay? R smaller to the first power, R larger to the second power, times 2/3. Correct? Let me see. Times 2/3, right? That's the result of the theta integral here. So this is going to be 2/3 of R smaller to R larger square. So I'm going to erase this thing here. Put this guy there. So the potential is going to be the phi is going to be 2 pi, right? So it'll be 4 pi here. Cancels that one. It's going to m0 divided by 3 a square, if I'm not mistaken. m0, 2 pi, 4 pi over 3, yes. So 3 square, r smaller divided by r larger square. So that's the potential anywhere on the z-axis. So on the z-axis, the potential equals to m0 over 3a squared. Is this right? I think so. I hope so. Let me see if the a square is correct. Wait. What is this? No. That's totally wrong. What the hell is this? There's no a squared on the denominator. Why did I put it here? It's a square. Sorry about that. A square, right? There's an a square that is in the upper, not in the lower parts. m0 a square over 3. Doesn't make sense, right? Right? So here, I think this is, let me see if it's right. A square there over 3, I believe it's right. So that's on the z-axis. So the solution anywhere, this is the L equals 1 term, right? So it's an expansion within a single term on the z-axis. You see that R smaller, larger, is the smaller or larger between, in this case, magnitude of z and r, right? In fact, I can use z because I'm using z larger than 0. I can make it between z and r. Okay. Because z is larger than 0, I can use that. I use these x's. Otherwise, if I was minus z, the angle would be different between x and x prime. So that's what it is. Okay. If I go now to the solution, given the solution on z, you only multiply by the corresponding Legendre polynomials, but we have only one, which is P1. So the solution is going to be M0 over 3 r smaller divided r larger square P1, which is cosine theta. That's the solution. Now, r smaller is the smaller and larger between this was before, before between z and a, right? Which is the radius of the sphere. Now it's going to be between r and a, for this case here. So for r smaller than a, the magnetic potential equals m0 a square r cosine theta over 3a square, right? So we cancel those. So you're going to have phi m equals m0 over 3 times z. The field now is going to be h equals to minus gradient of phi m. So inside the field is minus m over 3. M is m0 az. So the field inside is like this. Okay? And what happens outside? Well, outside we have a magnetic dipole, again, a point dipole at the origin equivalently, right? So outside, for r larger or equal to a, r smaller is a, so the potential is going to be m0 a3 over 3r square cosine theta, right? m0 a3 cosine theta divided by 3 r square, if I'm not mistaken, yes. And now the magnetic dipole is the magnetization times the volume in this case. So m0 a3 divided by 3 equals to m divided by 4 pi. So we have the magnetic potential outside. Again, that's the magnetic potential due to a dipole, point dipole. What is this? This is phi m equals to m cross ar divided by 4 pi r square. And the field we know, right? The field is going to be the gradient again, 1 divided by 4 pi r square outside anywhere, 3m dot ar minus m. That's the field outside. Okay. So outside, everything, have a sphere, replace the sphere by a point dipole with the magnetic dipole calculated like this. And the field is, the potential, the scalar potential is going to be that due to a magnetic dipole, right? Also, let's go back to the internal field. Internal field. So we are going to show you where are the magnetic charges. The field equals to minus m over 3, and the B field, right, equals mu 0 h plus m. The B field is going to be 2/3 of mu 0 m. Okay, so if you look inside, what happens? Inside, the H field is like this. H field, right? Uniform and points down. Magnetization is up. Magnetization like this. Constant. H field is downwards. And B field, where is it? Where does it point to? Well, the B field is up to, right? So it's something like this. B field is like this. So you see that the H field is an invented field. The real field is B, is this one here. H field is auxiliary field. But I mean, if you look at the B field, the H field, it's like you have a magnetic positive charge here, right? 0, negative here. The H field goes from the top to the bottom, right? Outside the H field, you see that H field outside is that to a dipole. So I'm going to you know, it's as if you had a dipole at the center. So the line, the H field line is like this, right? I'm just going to draw one. It's like a H field to a dipole at the center. The B field I mean, you see that there's a divergence here, right? H field looks like it has a divergence that is not 0, because here the arrow goes down, here the arrow goes up, right? So the H field is the fictitious field. The real field is the B. And B, if you look at B, B is the one that's green, right? The green field here. B field is like that. And this a closed line. That's the B field. Dipole, right? So it's not like this. Here remains constant. But you see, it's a closed line. The B field is the real field, magnetic in origin, which is closed lines. On the other hand, H field is a fictitious field, but it has an interpretation according to these fictitious magnetic charges, because we have a divergence there. Okay, so that's what we obtain using this alternative solution. Of course, so this is the you know, the same illustration I just did. You know, closed lines for the I think this is drawn wrong, huh? Yeah, this is wrong here. I'm sorry about that. This is on the other way around. The B field is not like this, but it's like that. Oops. My pencil just went off. Just a little bit of charge here. Just to conclude. So you have, you know, the B field is like this, as I drawn. Okay, yeah, this is correct. This is correct, like this. Okay. So, well, I mean, of course, we could have solved this problem also in a different fashion. We could solve this problem by notice that the Laplacian of phi, either inside or outside, equals to 0. Because inside, it would be minus divergence of m. which is 0. And outside, there's no magnetization, so there's no magnetic charge. So Laplacian of phi equals to 0, and obviously, because of symmetry, the solution is like this. We could use this procedure, right? PL cosine theta. Then we would apply this inside and outside in matched boundary conditions, and we would solve the problem. Okay? So this is the conclusion of our lecture. That was our objective, to show how to solve different boundary value problems using different tools, either vector potential in some situations in which the current is constant. When the current is constant, is going to, I mean, the direction of the current is constant is easy to solve. Sometimes when it's also makes closed loops, sometimes it's easy to solve as well. And also using scalar potential to show the versatility of different methods of solving boundary value problems in magnetostatics. So with this we conclude this lecture and hope to see you next time. Until then, bye-bye.